Hey, good Friday afternoon, everybody. Welcome to another episode of Houdini Secrets Live, brought to you by TechArt EDU, otherwise known as Little Old Me, Chris Rhoda, teaching you guys Houdini stuff and tech art stuff based on his past experiences, and so sharing out this. In fact, I was just getting ready my USD introduction that I created this morning, or actually kind of this early this afternoon, and I was just editing it and putting it together, getting ready to put it up on YouTube. And if you guys are interested at all of learning USD, side effects is big, very bullish into it, and so they see big things for it. And I myself think USD is like totally awesome and it has a huge amount of potential, and I'm really excited to see where it's all going. And if you guys want me to start teaching about USD inside of this Houdini class, get back to the Orlando Houdini Users group webpage. Go check that out and tell me, hey, I want some more USD in my diet. I think that stuff is going to be good. Mm-hmm. And likewise, if there's any other Houdini topics, please tell me. I do have to tell you that I am kind of running out of time because in the fall, I've got a whole bunch of new students coming in, and I got to teach them from the beginning. So a lot of my introduction will come from a lot of my classes will actually be introducing Houdini, but that is unless there's other people in the Orlando Houdini Users group area they want to discuss, and then we can get you guys involved in broadcasting too and putting out some content. And then we can bring all together, and so we can kind of split duties, and we can keep the advanced content, and we can keep the newbie content coming. Just thinking out loud. This could be a contributing thing. So if you feel that you want to contribute and you want to maybe teach some novices some Houdini, this might be a really good opportunity. And oh, speaking of teaching novices Houdini, if there's anyone out there who wants to who is a student and they want to contribute to the side effects um, educational package, get your video to me by July 1st, because I need time to to cut everything together and to make the video and put together the presentation package, which has to be done like on the 5th or something. And so I'm going to need that 4th of July weekend to put it all together. And if you don't send me your package by then, I'm not going to be able to get it in, and I need 7. I need 7 students to submit stuff. Because otherwise, if I don't have 7, side effects is going to go, University of Central Florida is too small. We're not going to let them be a Houdini school. And you guys aren't going to get your Houdini licenses. Damn it. Okay, we got to get you some Houdini licenses. Come on. Okay, get in contact with me if you're going to submit something so I can look out for it and be aware that it's coming out there. All right, cool. Get it to me at Chris at TechArt EDU, or if you guys also know me, Croda, CRODA at UCF.edu. I can be contacted at all of those places. So send me your stuff, and if you're gonna be sending stuff, warn me ahead of time. Throw me a say, hey, I'm gonna be sending you some stuff. I would appreciate it. Okay, let's get on to this. All right, we're getting along in the tooth with this procedural tree business. Hopefully, we're just about nearing the end of things. And today, what we're going to do is, oh yeah, I wanted to add a little gravity to the trees because they're not looking so, they're looking not kind of like organic enough. But there's a lot that we can do to these trees that you can custom make, and there's a lot of things that you could do. So if you have any ideas or any things that you want to do, then just tell me, because there's just too much time, and I'm spending all my time teaching you guys fundamentals. All right, and then we're going to add some leaves. Okay, we got some leaves and some gravity today. So that's what we're going to be doing today, hopefully, and then we might be finished with the trees. All right, let's get going here. Okay. Now, hopefully you guys should see the nice Houdini screen for that. If you need to use the content that we created last week, go to the Orlando Houdini Users Group page on GitHub and download the 619 content. And that will get you up to where we are right here. All right, now notice that our tree here is looking a little bit stiff. It kind of looks like, you know how you go to like Walmart around Christmas time and then it sells some of those like kind of like trees made out of like hardwood or they're made out of white pipe, pipe cleaners. Well, that's what this kind of looks like. So let's go put some gravity into it and, get it, working with some gravity working on it. But before we can't just apply just gravity to it. We have to think about what we want to do it. We want gravity to be very, very soft right at the beginning of the branches because that's going to be like where the branch is the toughest. And we want gravity to be the most effective, like at the very end. So we want to create a gradient from the beginning of the branch all the way to the top of the branch so that the effects of gravity can take hold. And so that is how we are going to perform on it. All right, so we're going to go drop inside of our tree SOP or tree digital asset. Ooh, it's getting big. All right, and so insert a attribute wrangle between the is trunk and the copy to branch point. Okay, so what we're going to do is we're going to introduce another attribute wrangle. Okay, we're starting to get advanced, gang. And the more advanced you get, the more you start using the attribute wrangle SOP because it is just such a convenient SOP. And I'm really glad I had the opportunity of teaching you guys Vex, as my first lecture here because it's a really useful tool. So let's go ahead and drop an attribute SOP. Oops. And attribute wrangle SOP, there we go. And yes, by default is with points. So we're going to say, we're going to call this base pause. Short for base position. No, I want to get this base pause. My group, I don't have a group named base position. It's not going to like that. But here's our Vex expression. All we're going to do is just give it the point position as the base. So basically what this does is it puts the very first point position as the base position. So V, if that means vector, at base pause, that means we are going to be creating a new vector attribute that goes into the class equals at P semicolon. If I hit Alt and then Enter, all right. So I like to watch where my data goes. So I'm going to go over to Viewers, Inspectors, and then Geometry Inspector. And then we see we have a new base pause attribute here. And this basically is the same thing as my position. All right, cool. Good enough to go. All right, we're gonna use that much later on today. All right, so now what we're going to do is drop an attribute promote SOP between this copy to branch point and the spine end here. We're gonna be playing around with this. There's a lot to do in this section right here. This section right here has a lot of opportunity to play with because basically we've cemented the branch onto the old trunk and now we can start doing things with it. And this is what we're going to do is we're going to put some gravity on it. So we've got that gravity. So I'm going to go create an attribute promote. All right. And you know that base pause that we just created? Yeah, well, what we're going to do is make sure, okay, we got base pose, yeah, base pause, and it was a point, but where we're going to put it, we're going to move it up to the primitive because we want to behave this base position on the primitive hole. Look at that. Houdini identified it and enlightened it for me. Oh, okay, thank you very much, Houdini. I didn't know that we needed that. But as for the promotion method, make sure to get first match. There we go. All right. Now we're going to apply the gravity force. Now, as mentioned before, we just don't want to shift the vertices along some kind of gravity vector. What we need to do is distribute the effect over the entire length of the branches. So the points closest to the base have the least effective gravity, and the points furthest away feel the most part of gravity. So what we're going to do is add an attribute wrangle SOP between the attribute promote and the spine end here, and we're going to create another attribute wrangle. You know who really likes attribute wrangle SOPs? Anastasia Apara, and her stuff is phenomenal. If anybody wants to study some practical examples in computational geometry, focus on her stuff. It is dizzying. Anyway, you get to learn how to use the attribute SOP, reverse engineering some of her stuff for sure. Anyway, we're going to call this apply gravity. I'm going to have to see if I can get her to be a guest on Houdini Secrets Live one of these days. I don't know her perchance, but I might just have to introduce myself to her. Anyway, we'll get her onto it. So let's go ahead and write this function. Now this function has got to be a little bit big, so we're going to give ourselves some room here, but it's not really too bad. So we're going to start off by, let's see, do we have, before we go ahead and edit this, let me see the interface. Here's our tree dev. And there's my tree gen. So branches, trunk, branches. Okay, you know what? I forgot to create a folder here for gravity because we have no thing. How do we go to do with gravity? Okay, so let's go ahead and add some stuff for gravity here. So I'm going to right click on my tree gen, go into type properties. Come on. There you go. All right. So here it is, branches. We already have branch length going on here. So I'm going to grab a folder and then toss that into branches. And then I'm going to call this folder gravity. All right. Now I can't remember all the parameters, but I knew I'm going to need one thing for direction. For the gravity has got to take on some kind of direction. No, I'm not actually going to do a real gravity simulation. It's going to be a total fake, but we still got to have some kind of direction. So I'm going to grab a float vector 3 and put that right underneath gravity. And I'm going to call this what do we call this? Gravity direction. So call gravity, what the hell, call it gravity direction. Gravity direction. And the range, -1 to 1. Yeah, that seems to be about right. Well, let's make it -5 to 5. That might be too much. We have to change that. And for the initial values, let's keep them at 0. All right, so here's our initial gravity direction. We want it at 0 because we don't want to have any kind of effect by default. We want it to stay in place. So let's grab a float here because we need some kind of scalar in order to control the amount of gravity. So I'm going to grab float here. And for the, since I'm going to give it a default value of 1 before going over to my parameters. And let's give it a name for, we'll just call it gravity. Gravity, huh? Gravity. And then as a label, call it gravity scale. All right, I can't remember if I need any more parameters than this. But right now we have gravity direction, goes between 0 to 0, and gravity scale. That's good. All right, cool. Now let's go ahead and go to our apply gravity. So we're going to go and first get our direction. And I'm going to take a shortcut here. So I'm going to say vector direction equals CHV. And I want to call it local case dir. Okay, why did I create that? Well, I just wanted to create a local variable for direction, and then I'm going to, once I get it working locally here in the attribute wrangle, then I'm going to promote it up to the SOP level through the variable that I just created, and it's just going to be an ease of access here. So if I want to hit Alt-Enter, and then nothing happens, so that's fine, but if I come over here and hit the plus with the slider in it, it creates a brand new interface device right here. Okay, that's what we want. So we're going to go float dirmag, that's short for direction magnitude, equals length of direction. Okay, remember that direction is a vector, so it's got 3 values, x, y, and z. So what we're doing is taking the Pythagorean theorem, x squared plus y squared plus z squared, and then we're going to take the square root of the sum of all those, and that's the length. And that's what we have here. And then what we're going to do is use that. We know the length, and so what we're going to do is we're going to normalize direction. And I could just normalize direction by saying slash equals dirmag, but I'm using a division, and that could be problematic if I ever goofed. So instead, I'm just going to say direction equals normalize, and it's direction. Because then I know Houdini's smarter than I am. It's not going to ever return 0. All right, cool. All right, now what we have to do is figure out the number of points that we have to deal with that are coming in. So I'll say int my prim equals points point prim point prims. Okay, so what this is Mr. Prim. I say my prim. Okay, so what this statement is doing is that this point may be attached to multiple primitives because it's could be a vertex and so forth. So what we're going to do is use this function to list all of the primitives that this particular point is associated. But since we're dealing with a straight line, we're only going to be dealing with one primitive. So we're just going to get the first value. So we're going to go at ptnum, which is the current point number. So the point prims says return all the primitives that this point is attached to, and we want only the first one, so we're going to give it a index of 0. All right, cool. So we now have which primitive our core point is attached to. So that's good. So we can use that in order to start looking for stuff. So let's look for the base position of our branch. So we'll go vector. Okay, prim base. So what is our primitive base? Equals prim. That means get primitive information. And our input is at op input 1. And then what we're looking for is base pos. You see, now this is the reason why we created that base pos parameter. Base underscore pos and my prim. Okay, no errors so far that we are going. So this returns the base point of our primitive, so that we know that. You know what? I have got a sneaking suspicion that I did something wrong. I don't know. I just got that itch. that feeling in me. So I'm going to add a printf statement just to make sure that it is working. So go printf, primbase equals, okay, $f, %f /n, and then comma, and what we want here is primbase. All right, if I hit Alt Enter, then let me take a look at my, okay, primbase. And you'll see that the number all shows up the same until we change the, so it's repeated a bunch of times because this is the location of each of the points of each of the branches. And so I've got about 50 or 60 branches here. Okay, so this is working. I'm going to comment this out so that I don't have to look at it anymore and it'll stop printing things out. Okay, so we've got our primbase information working properly. So let's go ahead and continue. Give me some room here, dang on it. Now I'm trying to create. Okay, so I'm stuck with this window. Daggone it. All right, give me the delta. Give me the distance between the current point and the base point. So vector delta equals at P means the position of the current point that we're looking at minus its parent primitive's base position, so primbase. Okay, that's going to return the delta. And then we're going to find the length of this delta. So float delta length equals length of delta. Okay, that's not so bad. Okay, not too bad, not too, so far we're doing good, I hope. Okay, now what we have to do is figure out how much gravity should be proportioned. So what I'm going to do is we've got a vector that we're coming in from our direction. And let's just say that this vector, give us some room here. Come on, there we go. Yes. All right, let's put some values in here. Let's go like -1, and then x is like 0.5. Okay, so it's coming right at the screen here. So this is a vector, right? And this delta is a vector from our point down to the base. So we want to figure out how much gravity should be enacted over that entire segment. Let's suppose at this point we're looking at here and delta here, so that means my delta vector is here, and my gravity vector is over here. So how do we figure out how much gravity to apply? Well, what we do is we project the delta vector onto the direction vector. And for those of you that fell asleep during tech art class, we do that by getting the dot product. The dot product projects one vector on top of another, and it returns a float. So how much gravity should be considered? So what we're going to do is we're going to do a vector offset, vector point proportion, PT point proportion equals dot. Well, actually, this is a float. It should be a float. Because a dot product always returns a float. It doesn't return a vector. And delta and direction. Okay, delta and direction. All right, very good. Then what I'm going to do is I'm going to figure that out and get the gravity impact. And we're going to do that by subtracting it from the original delta, and then we're going to multiply it by the proportion here. And So there we go, gravity impact. So what we have here is delta minus the original direction times this point proportion. Let me double check to make sure that I spelled this correctly. Even though I spelled it incorrectly, I'm just propagating the error right here. Okay, so there we have as our gravity impact. So now let's go figure out what our offset point is. So vector offset point equals at P, which is our current position, plus 0.025 times gravity impact times Dermag, which is the length that we just computed up there. So gravity impact times directory magnitude times the direction. Now remember, direction is a normalized vector. So that's why we multiply it and change its shape around in order to give it some overall size and shape. All right, so now we've got our offset point. So let's get our new delta. So vector new delta equals normalize. So what are we going to be normalizing? Offset point minus prim base. So we have our offset point minus prim base. Okay, that gives us the direction of the base to the offset point. Now, let's just do offset point equals prim base plus new delta times delta length. Okay, see, we're pulling it all together. And then we could just say at P, so that means we're going to modify the point position, equals offset point. Ah, look at that. Our tree shifted around. Uh-oh. Hopefully it's not crashing. Okay, save as. And we're going to call this 626. Okay, look at our tree. It's now going off into the kind of like negative X, positive Z direction. And so if we wanted to play with this some more, we just manage that and we just move it around. Okay, so it's taking on kind of like a more type of experience here. Okay, and so it's kind of like causing everything to kind of like bow in this direction. All right, so we've got this controlled. So let's go ahead and multiply times the parameter that we promoted up on our digital asset. And I can't remember what they're called again. So we've got our tree gen, our gravity. So we have gravity direction. Okay, guard. I spelled that with a capital G. Shame on me. Okay, we'll just leave it as is and I'll call gravity. All right, let's go and do it. So let's make this CH, open parentheses, close parentheses, open and close quotes, dot dot slash gravity direction X. Yes. Okay, so I'm going to grab this, copy and paste it. All right, I'm going to hit tab and then go with Y, change this to Y, and then go over into my Z, change that to Z. Okay, there we go. Okay, so now we control it from up there. Now, what do we do with that scale, for that gravity scale? Well, look at here. the original author of this just multiplied it by 0.025. And that, you know, increased or decreased the amount of impact of the gravity. So let's change this 0.025 to just gravity. So CH, open and close parentheses, times, and then inside of that, open and close double quotes. And then we'll go ... / gravity. Okay, so nothing changed because our direction is 0, so nothing really at all. All right, so let's see what happens when we go and manipulate this. Up there. Okay, so we have our gravity direction. All right, so if we add a little, whoa, I was afraid of that. Look at that. That is huge. It caused a huge impact. So let's knock this way down to 0.25. Okay, so it's a little less. And let's bump this down to like 0.1. Okay, so there. So you can increase the amount of gravity by just by playing with that. Boy, that is sensitive. Oh, but it works. All right, cool. All right, I'm going to go ahead and save that. File, save. Okay, we are good to go. Okay, gang, that is how we added gravity to the situation. Now, the last thing that we want to try to do is we are going to prep the thing for leaves. Now, we do have to do some preparations because there's a bunch of stuff that I didn't do that will get us ready for the leaves. And I'm looking at this and I'm not seeing enough curvature in my upper limbs. I might look at my formulas a little bit later. I just realized that this thing's carving pretty good, but these, not so much. So I'm going to look at my formulas to see if I can, if I find anything, I will send you out an update. And if not, then why don't you go ahead and fix it and tell me. I'll give you a guest interview on Tech Art Talk Live or on Houdini Secrets Live. Woohoo! Yeah, now we're playing with power here. Okay, we're going to open up the type properties of our thing. All right, we've got trunk, we've got branches, we've got bark, and we have leaves, but look at that. We've got nothing under leaves. So let's go ahead and put some stuff under leaves because I know that we're going to need it. All right, so drop a folder under leaves because we're always going to subdivide this into two things. We're going to try two folders here, one for geometry. So I'm going to type geometry in here. And this other one is going to be geometry. And then I'm going to drop one more folder in here. And I'm going to call this one scatter. Scatter, because we're going to be scattering a bunch of points on here to be the places for the leaves. Okay, now we're going to drop two floats underneath the geometry. So where's my floats? All right, there we are. I'm going to drag two floats under here, drop them under geometry. Uno, due. Okay, so we're going to call this first one min-u. Min-u. And that's short for U as in far as like UV direction. So this is the minimum amount of UV direction that we want to spawn leaves. And I'm going to call this leaves. I'm going to call that, the name is min-u, but the label I'm going to call it leaves start. And for the channel here, I want the range to go from 0 to 1. And here, I want to make sure that this is definitely 0. And now for the second one, I'm going to call it max U. Max U, because this is the maximum. This is the maximum place where I want leaves to spawn. And so we're going to max U, and we'll go label, and we're going to call this leaves. I'm just going to call it end. Actually, here's a sneaky thing. Okay, what I want to do is make these like connected with each other, but I don't want to create a vector. I just want them to look like a vector in the interface. So what I could do here is where it says leave start. So on the label, I can say, oh, I'm going to use that for both of them. I'll say leave start / end. All right. And now check this out. Now when I hit leave start, and if I hit the horizontally join next to parameter, if I click that and click this here, I'm going to not put any label whatsoever, but I'm going to leave that at max U. And I hit that at channel and put that to 1. If I hit apply, check this out. All right, so here it is, leaves. Here we go, leaves, start, and oh, look at that, max U. It put it together. I didn't realize it was going to do this. It put max U, the name, on there anyway. So, oh well, I thought I was going to be smart. Backfired on me. Oh well. So get rid of the end here. I'm still going to join the two together here. So I'm going to put just end. And then hit apply. Does this make it look better? Yeah, leave start and 0, 1. Okay, yeah, that works. Okay, cool. So we got to tell it how many leaves do we want to hit. And since number of leaves is an integer and it's not really a floating point value, I'm going to grab an integer and drop it under geometry and call it n leaves. N leaves for number of leaves. Number leaves. Okay. Range. This could be like, wow, anything we want. I'm going to turn off the range here. When I adopted this from Jerry, he had 25,000 in there, and that is a lot. And I found that working with just a few leaves at a time was much easier. So I'm just going to put this at 250 leaves, and if all is necessary, then we can really crank that up. Okay. All right, we'll come back to this. Now what we're going to do is now we're going to drop a float, a float vector 2, and this is going to be for the scale of the leaves. So geometry, and I'll call this leaf scale. Leaf scale, and my label, leaf scale, and where do we want the the range to go to? Is between, let's go 0 to I don't know, 5. Why not? Okay, but the channels, let's just leave things as is. 1, 1. Okay. All right, what else do we need here? We need a leaf, we need a seed value because we're going to have our own seed generator just for our leaves here. And so I'm going to grab a float and put it under geometry, and I'm going to call it leaf seed. Leaf seed, and that's going to be my label as well. Leaf seed. All right, we've got that, and our seed, that could be, it could be anything. So the channel value, I'm going to go with a good old 76.84. There you go, can't go wrong with that. I'm going to hit apply. All right, everything's looking copacetic there. Nice. So let's go ahead and add elements for the scatter. All right, we're going to drop an integer in for the scatter. And this is going to tell us, because we're going to be using the scatter operation, and we're not going to create our own this time, we're going to use the one Houdini gave us. We're going to be dealing with the amount of relaxation iterations. So we're going to provide that with one of the parameters. I'm going to call it relax iterations. And we make that to be the label as well, relax iterations. And, oh, Jerry put this at a value of 38, so let's go for it. All right, we've got that in there, and so let's create a radii scale for in the scatter. That's give me a float. And so this is called radii scatter. Radii scatter. Okay, yeah, this is a parameter required by the scatter SOP. Radii scatter. And let's put it in a default value. Well, let's put the range here between 0 and 1. And the channel here, let's make this 0.574. Oops. 0.574. Groovy. Now hit apply. All right, everything is good. We have got our scatter, just 2 floats, and our geometry, just on that matter. Okay, cool. Now, before we go in and start populating the world full of leaves, we got to do one more thing, and I call this old ghosts, because we have to go back in to the homemade scatter SOP. You know where we were, remember back then? All right, we have to keep track of how far along this is, but as far as the leaves are concerned, we aren't going to be able to get the information like we did here for gravity. We have to embed the data and send it to after it's had the bark put on. So we got to put it someplace where it'll maintain, and the best place to do it here is in the homemade scatter. So what we're going to do here is we're going to there's an attribute in here called grad, and you're going, where the hell's grad? Well, we create grad. Is it bark scale? I forgot. Well, oh, there, bark scale. Okay, yeah, grad is added on one of these. Well, that's what we get for not taking more fastidious notes. But anyway, it is in there. How do I know? If we click on I for the import, it is not in there. So what are we doing here? Okay, so well, I'm pretty sure that this works. So if I click here and click I, base pause, bark scale. Okay, bark scale is the one that I want here, and I believe that this is the value that I want. I think I've got 2 different systems going here, and I guess I have grad and then bark scale are 2 different vehicles. So the only thing that I see here, I don't see grad. Okay, so that must mean bark scale, because bark scale, you know, that if we look at bark scale here, all right, if we click here and say, look at bark scale. Okay, I may have been able to solve this. I don't know. Okay, well, what do we do? So we know that the grad goes from bark scale, okay. Okay, so there I go. That's what I get for working on multiple machines at once. I never transfer over the same information. I'm going to go in and check my notes really quick and say, where is the grad? Yeah, I figured as much. I forgot to put something down in my notes. All right. Yeah, the reason why grad isn't in here is because we never created it. And we create it right here where it goes in initial bark scale. So here we have the bark scale here. What we're going to do is create a new float here called grad. Float at grad, because we want this to be an attribute, equals the point num, so at pt num divided by num point minus 1. Oh, that's a at num pt minus 1.0. All right, cool. Now it's going to create that. Now notice that we created it here, but it's only going to be going through once here because it's stored in this information. If we click on here, here we have as our grad. Oh yeah, it's let's go back to go back into history and show how to do this. Okay, if we go up to 1 tree gen, and we've got the number of branches, we've got 3 iterations, but let's just say it's 1 iteration here. So all we're doing is just dealing with the center spine here. Then we're coming through here, and we know that by the end here, our grad is going to go from 0 all the way up to the tip here. Okay, so we know that that's the case. But as soon as we add a second iteration layer, what happens? Well, this old geometry, I forgot that it gets blasted away. So all that we have are those points here, and then we have to, and we allow on the loop, the feedback loop, to add to this. And so what we do here is we notice that we have input here. So we have grad coming in, but now what we're going to do is we're going to go into the homemade scatter. And so we're going to create a whole bunch of brand new points. And check this out. Grad is now automatically 0 for all the new points that we create. And so when we come over here to blast away all the thing, we blast away the old information. What happened to all our grad information? It's gone. So it never got propagated to our children. So what we need to do is go back into the homemade scatter and then make sure that our grad information gets copied through appropriately. So it makes sure that we get the interpolation properly like. So here we have here, I'm going to go, all right, so we have the open grad, and it's just a point attribute. So grad is a float, so I'm going to need float called current grad. All right, good. That's coming through here, and now we go into our loop, and so we have current point in there. So just as we did a prim attribute and we got the current position, we're going to do the exact same thing, and we're going to grab our grad information. Put that in there. I'm going to click that right in here, and I'm going to hit Control V, and instead of current pos, we're going to send that to current grad, and the parameter that we're looking for is just grad. Okay, what are these other parameters for? This is the primitive number that we're currently dealing with, and this is the position in U that we are currently examining, and this is a default value here. So this is going to go into current grad. Now we've gone through, we've got this new current point, we've created a new point, and one of the first things we do is we add a point attribute for U value, but we're also going to add a new attribute called, lo and behold, grad. So we're basically making grad kind of like defy death. It's going to jump the chasm. So grad, but we don't want the current point in there because current point is a vector and we just need a float here. So grad, current grad. So we're going to call it this one current point. We're going to call this one current. Oops, it's going to barf. There we go. Implicit cast from float to an integer. Okay, well, that's not cool. Current point, geo self grad, U. Okay, so current grad is a float. And set point attribute to grad. Oh, I know what's wrong. So it's looking for the current point number. And we're going to use current point as the current point number because that tells us which point we're going to be accessing. But then instead of U, we're going to say, okay, we want our current grad value. All right. All right, cool. Look at that. Now we have our old grad values back. Yay! And then so as we look over here over to spine end, then we have grad has lots of grad values that change over time. Yes, that is what we want. Very good. Okay. So let's go and make ourselves some leaves. We've got our grad information now. So now we can go and add ourselves some leafage. All right. Oh, one more thing. Jeez Louise. All right. It says go into the spine loop and insert a point wrangle after copy to branch. All right. And then we're going to have to keep track of the level. All right. Inside of the algorithm, we have to keep track of the level. If you forgot the level, that is what kind of information that we want. We have to remember, okay, if it's level 1, it's just the trunk of the tree. If it's level 2, it's one of the boughs, and if it's level 3, it's one of the sub branches and so forth. All right, so what we have to do is change, what we wanted to do is tell each point which level it is. And we have that information already. Remember we created this spine info? This spine info has the iteration number already on there. So this is already it. So what we're going to do is just promote that value up into here. So we're going to go into a point wrangle. And then we're going to say I at level. So we're going to add a new integer attribute called level equals, and then CHI. And then we're going to grab our spine info. And let me make sure I get the spine info here, and just in case I get this wrong. So I'm going to go ahead and right click on iteration and say copy parameter. I want to make sure that I get the spelling exactly right here. Yes, I know. I'll put that in here. Now right click and then say paste relative reference. And it added some kind of wild, funky character there that I've never seen before. Okay, that's a not good. We don't want this. Oh, CHS. Oh, we don't want that. All we need is just the path. Okay, so did this give us some iteration for the branch levels? So we come over here, level, we got level 0 for the first ones, and then it goes to level 1. Yeah, and the rest of them are level 1. If we were to create further branches, it would go on to level 2 and then so forth. All right, cool. That all works. Yeah, I mean, like you'll notice that we kind of like go to point wrangle by default. After having talked with some of the side effects higher ups, there is a thought of that in a future version of further version of iteration is to make Houdini really just all about Vex. Just write Vex code for the whole thing, and that could be what Houdini evolves to in the future. Will it happen? I kind of doubt it. I mean, like people like their point networks and so forth, and it is kind of nice to follow along and visually see the patterns. So I don't know if that's going to happen or not, but you could almost start to do that by hand anyway. All right, good. Now he said, I'm going to go ahead and save this. All right, cool. Now, let's see. Okay, where are we going to create this? Okay. All right, so what we're going to do is we're going to create a subnetwork. And our subnetwork, we're going to need information from our bark and we're going to need information from our spine. So I'm going to create a subnetwork. I'm not going to create an extra digital asset out of it. I'm just going to keep things simple. We could create a digital asset out of it, but I'm not going to just because I'm lazy, I suppose. But we're going to call this one Make Leaves. And my input 0 is coming from my bark. I'll call it UV quick shade, and my input 1 is coming from my trunk and branches. All right, groovy. Now let's double click to go inside. Okay. Now we don't see anything here right now, but that's okay. If we have to, then what we could do is lay down a context, a viewer, the viewing context view, and then when things start happening, it'll show here. All right, so what we're going to do is we're going to work off the spine, which is this value, trunk and branches here. Okay, I'm going to create a null just so I know that I'm working off the spine here. And so null. There it is. We finally have something. There we go. There's our branch. Okay, good. You didn't think we had gone too far, do you? Okay, I'll call this trunk and branches. Trunk, branches. All right, and I like to color it yellow because it's input, and I change the shape. I say, okay, so this is coming in from up top, so it's coming in. All right, trunk branches, geez Louise. Okay, we've got trunk branches coming at us here. All right, now I've got this. Now what I do is we're gonna delete all of the branches that aren't trunks. That's right. So no, I mean, in other words, we're going to delete our trunk and we're going to keep our other branches around. And how do we know if the primitives coming in are our trunk or not? Well, it has a level. If it has a level of 0, well, it's a trunk. If it has a level of 1 or greater, it is a branch. So we're going to keep that. So I'm going to add a delete SOP here. Okay, we've got our delete. I'm going to call it delete non-leaf levels. Delete non-leaf levels. Okay. And then what I'm going to do is like, we've got this working here. And then we're going to say, well, let's add one more parameter. Now, I didn't create this, Jerry did, and it's kind of a cool idea. It's a little bit wonky, but it's actually a really cool idea. But he wanted an extra interface here right above group. So what he did was he right-clicked on this bad boy, and he went to parameter and channels, and went to edit parameter interface. And this looks like it's a digital asset interface like we were doing, but it's not. It's just an interface thing. And what we're going to do here is we're going to grab an integer, and then we're going to grab it right here and put it right at the top here. And then we're going to call that min level. Min level. And we're going to call that minimum level. And let's see, we're going to leave that at 0. All right. Click accept. And you see it created it there. So this basically, it will tell us what the minimum level that we want to start seeing breezes are. So we're going to say min level equals CH, and then open and close parentheses, and open and close double quotes. And inside we're going to go ... // branch levels. Oops. Daggone it. Branch levels. Okay, we've got branch levels coming at us, and then we're going to subtract 2 from it. All right, so this is going to still end up with 0 here, but so we're going to allow the branch levels of our interface up top to control this guy. All right, so why is that good? So we're going to go in and where it says delete selected, we're going to say, delete non-selected. So it's going to delete everything because we don't have anything selected, but we want, for the entity, we want points, and inside of the number folder, we're going to make sure that this is enabled, and we're going to delete by expression rather than pattern. And what's our expression? Well, right now it's 1, so it means select everything, but we don't need that. We're going to go at level is greater than or equal to CH min level. Okay, so that did not do what I was hoping it would do. It worked on my other, okay, so let's see if we go -1. Yeah, that's what we wanted it to do. All right. So now what you see here is we've deleted our trunk. So now we have as our auxiliary branches. Now, if we were to add more branches, we move up to 2. There they all are. If we bop into here and then go back into our tree network, and you see there they all are. Right? Okay. Beautiful. All right, so we've deleted everything but our, we deleted our trunk, and so we now have our leaf-bearing primitives. All right, so let's go ahead now and control where we want to actually birth our leaves by. And we're going to do that. We're going to add a carve sop. Now, a carve sop originated back in the days when NURBS ruled the land, but NURBS can be used for polygons too. And in this situation, you'll see that there's got a little point here, and this begins at the point here. Now, if we move this point around, you'll see that this actually carves away part of the line here, right? Pretty wild here, huh? Okay, now we're not going to leave this first U here just as this. Remember, we actually can control that from the promoted interface value up here. So we go CH, open and close parentheses, insert, open and close double quotes, and we're going to say // leaf start. Oh, it's capital leaf. Oh, what is it? Oh, daggone it. What is it? What is it? What is it? What is it? I thought it was leaf start. I'm being lazy. I should just go look it up. Oh, max U and min U. Yeah, that's what I called it. All right, that's what I get for bad variable names. Okay, min U. There we go. All right, now, so our interface now controls the minimum U, and we're going to, so this is the first U, the second U is the top value. And now you see that this controls the other part of the length. And I go CH, open and close quotes, parentheses, insert open and close double quotes, // max U. Max capital U. All right, cool. Now we're controlled by this, and now we can control the length of each of our little primitives of where we're going to be birthing leaves. So now let's go ahead and add that good old scatter sop. What we're going to do here is for each one of these points, we're going to insert a bunch of other points, and these are going to get scattered. And so we've got that there. I'm going to put that, and you'll see that there's a whole bunch of points in there. Now it has a total force count of 1,000. And well, let's see, generate by density. Yes, we want force total count. Okay, we created the number of leaves there, so I'm going to go, once again, we're going to reference our digital asset interface. So CH, open and close double quotes, insert, open and close double quotes, go dot dot slash n leaves, and leaves. Oh, look at that. Smoke and crack again, commas. Dot dot slash dot dot. All right, so there's about 250 leaves here. Is that right? So if I click over here, yeah, 250. Yeah, so that controls the number of points here we've got here. And now for our global seed, let's create the wild, wacky expression with our leaf seed combined with our master seeds. So I'm going to hit Alt-E to bring up my interface so that you guys can see it a little bit better. But CH, open and close double, open and close parentheses, insert open and close double quotes. I'll go dot dot slash leaf seed. Okay, and then I'm going to add that to CH, open and close parentheses, insert open and close double quotes, dot dot slash master seed. There we go. Okay, accept. Yeah, all right, there's our global seed value going in there. All right, cool. Now we have to do is get our relax iterations. So it's CH, open and close double, open and close parentheses, insert open and close double quotes. And inside of those double quotes, we want dot dot slash relax iterations. Thank heavens for point completion. Yes. And then we're going to do the same thing with scale by radii. So CH, open and close double quotes, open and close parentheses, insert open and close double quotes. All right, we want dot dot slash radii scale, radii scatter. Okay, and then I guess we're just being lazy here. And we're just going to put 13.4 in the value of the max relax radius. Okay, cool. Now, what is the impact of that? Well, let's see. Let's put the display on here. Okay, here you can kind of see the impact of the leaves, of where the leaves are going to go. And so let's play with our leaves and play with our scatter. So if we play around with the relax iterations, that doesn't change anything, but if we change the radii scale, you see that they tend to clump together. And then if we increase this value, then they tend to go apart. All right. Good. We've got our scatter. Now, what we're going to do is we're going to put on our mad scientist helmet, and then we are going to put crazy rotations on each one of these points. And we're going to point the normal somewhere along this. And that's okay. We're just going to create some crazy point rotations for the normal. Now, I have to give Jerry credit. He came up with a algorithm that's just more robust than what I'm going to give you. But honestly, I was pressed for time, and I didn't have time to reverse engineer all of his math. So I got a little bit of his math, and it's a little bit of nuttiness, and you can kind of see what we're all doing here. Okay, so what we're going to do, we're going to grab another point wrangle. Yes, sir, you knew that was coming. Go point wrangle. What's it doing over there? Hey, you. Come back here. All right. Okay, first what we're going to do is we're going to grab our seed value. So int seed equals CHI, that's because it's an integer, open and close parentheses, insert open and close double quotes. Inside of that, we'll go dot dot slash leaf seed. Leaf seed, okay. I'm going to terminate that with a semicolon. All right. And then we're going to create one for angle. So float angle equals radians CH, open and close parentheses, insert that open and close double quotes, and then we're going to put angle in here again. And then we're missing one more parentheses, semicolon. Okay, you're probably going, hey, wait a second, what in goody goo goo is that? Okay, what this is it's calling a channel that has yet to be created, and we're going to call it angle channel. And since we had CH angle, we're going to go and hit this plus slider, and that's going to create that new parameter for us right down here. And what we're going to do here is set this, okay, whatever the value here, we're assuming that it's in degrees, but we want it to be in radians, so radians transforms it into radians. And so let me double check. I think this value should be 60. I don't know. Hold on a second. Yep, it's supposed to be 60. All right, so then we have this angle that is basically the radians of angle. I think what Jerry was hoping to do is to make this a random variable at some time. So we might return that to someplace in the future. Is that we could put a random statement here and increase this angle here in order to give it some variation on a per vertex basis. So here's note to self. We could go ahead and create this. And in fact, let's put a note here. Could add more randomness here. All right. Okay, and then we're going to create a new float here called random angle. Float random angle equals radians, and then insert open and close double parameter parentheses. Inside of that, we go CH, open and close of that, and we're going to add another here called random angle. Random angle. Okay, we've got that random angle in there. All right, I'm going to have to change these, to promote these up to the top because I think we forgot to do that. So click, and okay, so could add more randomness here. Also here. All right, so hit Alt Enter, and I know this is supposed to be 90. So here we have is angle and then rad angle. Yeah. Okay, so we have just a bunch of random angles here. This is all kind of looking nutty, but what the hey. Now here's where we use our gradient value. Remember that value that we worked so hard to kind of resurrect and bring back from the dead? Well, we're going to use it here. We'll go float ramp equals f at grad. Okay, we're going to grab that grad value, whatever it is, we're going to grab it and assign it to our ramp value. All right, now we're going to play with a whole bunch of trigonometry, and we're just going to create some random rotations. So I'm going to create a value called phi, or phi, depending on which side of the Greek fence you're on. And we're going to go fit 0, 1. All right, so that means it takes 3 values here. It's going to take a floating value between 0 and 1, and it's going to fit that value, whatever it is, in between the next 2 numbers, whatever it provides. So we're going to come up with a random value. So fit 0, 1, we're going to go rand, open and close parentheses, and inside of that we're going to go at ptnum, so that's the point number, plus our seed value, plus 34102. Okay, does this number mean anything? No, but it's just a number that works. And this could be dorked with. All right, so we're going to get a random value somewhere between 0 and 1, which is cool because it works with a fit just fine. So we now have to fit it in between 2 numbers, and we want to set it between 0 and 2 pi. So comma 0 and 2 times $pi. $pi, is that right? Yes, sir. Okay, it doesn't give me any errors or anything, so it's good to go. So let's start playing Mad Dr. Frankenstein and start playing with some kind of crazy ass angles. So here, float A equals angle plus, and we're going to do another fit operation, fit 0, 1. And then we're going to do the same thing, but we're going to use, instead of 0 to 2 pi, we're going to use the random angle. So I'm going to copy all of this. And then I'm going to put it right into here. And then I'm going to change my seed value number instead of being with that all wackiness. I'm going to put some more wackiness here, 9001. Is that wacky enough for you? And so instead of 0 to 2 pi, we're going to go from negative random angle to positive random angle. So I'm going to change this one from negative random angle and change this one to positive random angle. All right, then we have this wacky value of A, and then we're going to multiply that by our ramp value. So that means is the further up the ramp we go, the further it is away, the more random the rotation is going to be. So float theta equals ramp times A. Okay. All right, so far, so good. No complaints. All right, now let's go ahead and create some random vectors for our normal value. So vector result. Well, actually, let's just put this into, because all we need is here at the end. So I'm just going to make it easier on ourselves. So let's just say at n, we like living dangerously, equals set. Okay, that means we're going to put in 3 values. We're going to add a new value here. So our x direction is going to be 2 values, a cosine of phi times cosine of theta. So cosine of phi times cosine of theta. Okay, there's our x parameter. Let's add a y parameter. So it's sine of theta. Sine of theta. And then a z parameter. It's going to be just the opposite as the cosine. Let's make it sine. So sine times sine. And let's put phi in the first one and cosine or theta in the second. Okay, well, we've got randomness in our ends. Let's see what happens. Let's go to the geometry spreadsheet and see what happens. We've got that. Let's take a look at our n. Okay, n's looking Kind of wacky. All right, so there should be about 250 points in here. Yep, 0 to 250. All right, so the true litmus is if we come up here and we turn on our vectors for normals, and are they going in different directions? Well, let me look at this a little bit easier. Let me increase my normal length in my thing a little bit. Where is that normal length? Guides, is it here? Normal, scale normal is 0.2. Let's make it a little bit bigger. Okay, there's our normals. Yeah, they're kind of going off in random directions. It's good enough. You know, let's see. We'll play with our. Let's see what impact these values do. If we play with our angle, is that going to impact anything? Yeah, kind of uniform like. And let's check out this rand angle. Does this? Oh, how disappointing. Well, it does. Yeah, it does a little bit. Yeah. Yeah, there's a little wackiness. Okay, 500. Why not? Okay, this is all randomness. You know, we're all having fun. Okay, cool. So we've got our random vectors all going off in wacky directions. But that's cool because what we're going to do is we're going to put new. But here's the problem. We have our trunk branches. But here's our trunk branches, and then we have all these vectors kind of like going off in wacky directions, which is cool, but we're not going to be putting the leaves actually on the spine. We have to put the leaves on the branches. And you say, well, okay, well, so what? What does that mean? Okay, let's take a look at this. Let's put a here for the bark. So I'm going to add a null here to off input 1. A null. There you go. There's our bark. And I'm going to call this one my barkness. My barkness. Barnness. No, not barnness. Barkness. Okay, I'm going to give it a color of course, yellow. And I'm going to give it a shape. Input. All right, there we go. Okay, why isn't it yellow? Color yellow, damn it. Okay, good. Now notice that for the smaller branches, you don't really matter so much. I mean, you can't hardly see it. But as the branches get bigger, you notice that the leaves are being born from the middle of the branch. So what we have to do is then project our branches, our leaves, to where they are on the bark. And I was like, how in Gunny Goo Goo are we going to do that? Well, remember, for all of those who don't know me very well, I'm on a big ray tracing binge lately. So what we're going to use is some primitive ray tracing. So I'm going to lay down, off of my point wrangle, I'm going to go lay down a ray sop. And the second input, I'm going to come from my barkness. And so what I'm going to do is I'm just going to project rays along my normal. And we're just going to go and project rays. And then we're going to ray combiner. And so what we're going to do is we're just going to the edge of the bark. And you'll see that our rays are indeed now starting from the edge of the bark rather than in the center. It's a little bit hard because everything's blue, but you can see the leaves starting over there. Okay, and so I don't want my original source, so show guide geometry, yeah, get rid of that. So yeah, there you go. There we can see it much better. So get rid of my guide geometry, and you can see that the leaves are now coming from the branches, from the edge of the branch, which is exactly what we want. All right, I haven't saved in a while. I'm going to go ahead and save. All right, cool. Now, admittedly, I was being lazy, and honestly, I'm one of those guys who, if I don't use my hand drawing chops, they start to get really weak. And so it was late last night, and we just got the internet turned on because the internet flipped itself off, and it was terrible. So what I had to do is I had to draw a very primitive leaf, and I was going from my memory because I didn't, yeah, I couldn't, I mean, my internet was down. And so I said, oh, what does a leaf look like again? You know, bare of little brain here. I'm kind of like suffering from massive delirium. I don't know what a leaf remembers looks like. So what I did was I drew a leaf here, and yes, excuse my, this really is programmer art here, gang. So check this out. I'm gonna drop in here a Photoshop image. I've got a Photoshop image here. Where is this Photoshop image? What does this look like? Let's see. All right, let's go into here. All right, it's fun. KPB broadcasts. Yeah, Houdini Live. Foliage demo. Text. Yep, there it is. I could not remember what a leaf looked like last night, so I just jumped on there and I drew a leaf. And now, how sad is that? But the important part, the important part is that this leaf has a stem, and this stem goes all the way to the bottom here. Because that's important here, because we're going to take advantage of that information that it goes all the way to the bottom here, and you're going to see why in a little bit. But draw yourself a better leaf. And so this is the template for a leaf. And so when you go in UE4 and create a leaf texture, make sure that your leaf texture looks something like that. All right, cool. So you guys get the idea. So with that said, let's go and resurrect this horrible thing. Drop in a trace sop. What is a trace sop, you ask? Well, a trace sop is if you put in an image into a trace sop, it will do its best to trace around that image. So on this image input, I'm going to go and grab it from my texture here. Text, there's my leaf alpha. Look at that. I mean, look at that. That was looking like I was smoking crack at the time. Jeez Louise. Okay. Now the threshold is, let's go see what this looks like. Oops. Whoops. Turn off the... There we go. Look at that. It's beautiful, right? Sweet. It's beautiful. Okay. Now the important part here is, let me turn on the origin, the gnomon here. It's not necessarily centered. Now we have to center this so that this part here is overall centered over the leaf here. So in order to get this to work, the first thing we have to do is rotate this bad boy 90 degrees. So transform. And we're going to rotate this 90 degrees. So it is now sideways. All right, now what we're going to do is add UV projection onto this. So UV project. And why would we happen if we put just UV texture on here and say orthographic projection? Oh, I think that worked. Did that work? I think I fixed a problem of mine. Oh, I think it worked. Well, we'll see. If this goes all the way to UE4 and its textures are all goofed up, we know where to go to. It's this guy. This guy's the culprit here. Look at here. All right. Now, what we're going to do here is assign a material for it. So I'm going to drop down here a material network. So got a tab. I'm going material. Labs, quick material. No, material network. That's what we want. And what am I going to call this? I'm going to call it leaf mats. Yeah, the materials that we're going to create here are just temporary placeholders because when we go into UE4, we're going to replace them with final UE4 materials. But I'm going to double click into the material network. And then what I'm going to do is I'm going to add a principled shader. So I'm going to hit tab and type in principled. Principled shader here, that's all we want. And I'm just going to call this temp leaf, because I know for sure this is going to get killed once we go into UE4 temp leaf. And for the base color, I'm just going to make it white. It's albedo. Just going to make it white. All right, good enough. That's all we need it for. Oh, all right, now let's put down a material node and then access that material. Okay, a material. Okay, you got the material, the group material, so I'm just going to go / leaf mats, and temp leaf is what we want. Okay, cool. We have a temp leaf material on here. Okay, good to go. All right, now we're going to adjust the position of the leaf. We're going to transform it to the center. So I'm going to add a transform SOP. Okay, for the translate X, we're going to go minus $CEX. And then I'm going to go here, that moved it over a little bit. And for the Y, I'm going to go minus $CEY. And then minus $CEZ. All right, you probably are going, hey, wait a second, buddy. What in goony goo goo is going on here? Okay, CEX, CEY, you know, I'm getting confused here. Why did you use a $sign? Why didn't you use it? Okay. All right. Okay, transform. This is for all you old school Houdini people. You know about this, but the old transform, if you look under here and click under the help, and hopefully it still has it, there's about a bunch of local variables inside the transform. And one of those local variables is a CEX, CEY, and CEZ, the centroid of the input. And there's centroid of the intergroup, there's Xmin and Xmax, there's a bounding box, and the size of the input. So here's some stuff that you can add access to that you didn't even know was there. And that's kind of taking advantage of that. All right, so I'm going to call this translate to center. Okay, now what we have to do is we are going to find the rightmost point. So here, the rightmost point is like right around here, but how do we find that? Well, what we're going to do is we're going to create, yes, another attribute wrangle SOP, and then we're going to check each of these points. And then we're going to compare them against each other, and the point with the greatest X value is going to be the winner, and that's going to be our rightmost point. So that's what we're going to do, is create a attribute wrangle to figure out the rightmost point here. So grab us an attribute wrangle. Okay, so we're going to create a dictionary to compare all the other old values that we go by. So float X dictionary, so XDic, and then we're going to put open and close square brackets on there. So that means it's an empty array. And so what we're going to do is we're going to go through all of the points one by one and collect all of the x values. So we're going to create a for loop, for, and inside that for loop, we're going to go int I equals 0, and then I is less than endpoints 0. So that gives us the number of points coming in from input 0, semicolon I plus plus. Okay, there's our for loop. That's going to loop through all of the points that are coming in. All right, so what we're going to do is we are going to, oh, I'm not going to do that to you. I'm going to be evil. It'll get a little bit more verbose, but it's easier to read. So we go vector pos equals point, and we go coming in from the first input, and then we want the P information. P, and then we want the ith information. That tells us which point number to access. So that gives us the point position, and then all we're going to do is append that to the X dictionary. So append xdic with pos.x. Okay, we've loaded up our X dictionary. So what do you do with it? Well, what we're going to do is we're going to go through the entire loop again, and then we're going to compare. We're going to figure out what the maximum. Actually, we're going to use Vex, and Vex is going to tell us, okay, what is the maximum value in the X dictionary? And then we're going to figure out which point it is, and then we're going to move everything to that point here. So check this out. Madness, kind of like crazy school Houdini-ness. So float root val equals max dick. Max x dick. Max x dick. Dictionary. Okay, root val equals max x dick. Okay, fine. Good. Okay, so this gives us the maximum root value. So this gives us the maximum x value. All right, cool. Now that we have that, then we're going to go loop through all the points again. Okay, we're going to create another for loop. For, open and close parentheses, integer pt, pt equals 0. pt is less than, it goes in the opposite. pt is greater than or equal to 0. And we go pt minus minus. Okay, so we're kind of going in reverse direction, but honestly, it's all the same. It's all good. All right, so what we're going to do here, we're going to grab our vector position of every single point. So vector pos equals point input 0. Okay, put double quotes. Instead of double quotes, put a capital P because we're going to get the position, comma, PT, because this is the point value. Okay, now we have the position. And then we're just going to compare the position of this new point against our root value. And if it does equal it, then we know we found a fine, and then we know how much to move by. So check this out. We're going to go if, open and close parentheses, pos.x equals root val Okay, that means we're going to go through, if we can find a match with the x value, then what are we going to do? Is we're going to create 2 new float values. So float, or f at move x equals pos.x, and f you guessed it, at move.y equals pos.y. How did you know we were going to do that? Okay, cool. So what happened here? So let's go ahead and hit Alt-Enter, and let's take a look. Did anything happen? Nothing happened. Okay, so what big deal? But it did create move X, move Y. Okay, something didn't happen right here. So something didn't right. Oh, okay, okay. So we never identified it, so something didn't happen here, so we have to debug. Okay, so okay, so we have here point is greater than 0 point. Oh, point equals 0 here. Yeah, this is endpoints. Yeah, endpoints. So we had to go for that. So it didn't loop the endpoints. 0. All right, hit N. Yeah, there it is. Yeah, I love this geometry spreadsheet. I get to double check my values here. So, but here, this is how much we have to move this by. All right, so we're going to add a another transform stop here. And I'm going to say move to left, move to rightmost. All right, so we've got this translate here, and we're going to go minus detail. Equals 0, comma, open and close double quotes. Oops, one thing too many. Open and close double quotes. Move X, comma 0. Is that right? No. So this is not a. This is here it is. This is not a. This is a point sop. So they're all going to be the same. Is this all the same? So are these values all the same? Move X, move Y. Okay, I did my math wrong, or I copied it to the wrong place. I should have made it a primitive variable. It doesn't matter. It's all the same. We can access this information just as well. So instead of using a detail, I'm just going to use minus, since it's all the same, point, open and close parentheses. We want so let's enable this one. Okay, I know it's okay. Let's keep this simple. Yeah, I'm getting more complex. All right, so we've got this attribute wrangle here, and so let's just put an attribute promote. Attribute promote. My brain is dead. I'm suffering from delirium. And so the original name, what we're going to do is move move X and move Y. And no. No, that's not what we want. Okay. Hold on. I don't know why I'm having such a hang up on this. I will be immediately right back. Okay, yeah, I know what I did wrong. I forgot to run this over. Okay, for this attribute wrangle, so we run over the points, so we wanted to go through all the points, but we wanted to go over the details, so we only wanted to go over once, so we want it to only go through once. We don't want to go through n squared times. So if we look here, we got the attribute wrangle. And now if we create any new attributes, what it's going to do is going to push this up to the detail level. So if we go over here to the geometry spreadsheet, okay, it's not going to be in the points. If we go all the way down here to the detail, there's move X and move Y. It's all the same. Like I said, okay, so now what we can do is move this along just to its right place. So minus detail, 0, comma, move X, comma, 0. And you'll see that just moved it over just a wee bit. And then we're going to do the same thing to the Y. Okay, there it is. Okay, now notice that the, maybe that should go up here. Something is not right. Oh, it's a capital Y. That's why. No, that should go back to negative. All right, there it is. So the rightmost point now is sitting at the origin. So now, guess what we're going to do? We're going to move we're going to copy leaves from this geometry onto this. But before we do that, we're going to clean this thing up a little bit and make it a little bit more presentable so that when we take it over to UE4, it won't look like shit and make it look good. Okay, so we've got the transform. We're going to drop that and we're going to pop in a resample SOP. It's going to resample the number of points here. And we're going to keep the level of detail 1, method even length segments, measure a long arc, and the length 0.06. Oops. And I'm going to undo that and type in 0.06. All right, and then I'm going to append a remesh SOP. We've got a remesh SOP in there, and so the iterations is we just want one iteration, and the smoothing we want to be 0, and the recompute normal equals false, so yeah, get rid of that. And the target size, make this, oh, good number is 807.807. So there you see, it retopologized our thing. All right, cool. Now, all we have to do now is just copy our leaf to all of our points here. So let me go and put this into a network here. Shift O, and I'll go make leaves. Make leaf geo. All right. All right, so we have our points here, and then we have our thing. So what we're going to do is copy this to points. So click here and go copy stamp. Because who knows, there might be some future iteration of some wackiness here. And so we're going to use this as the thing. So copy stamp, and then hit display. And, oops, turn off my normals. Why is it showing the, oh, because those are the points. Huh. What is it showing there? Oh, this is probably some kind of artifact I've got here. But you see, there's all my leaves going off in their variable glory all over the place. Okay, cool. So we've got that going. So let's go and drop this in here and add a null. And I'll change this shape. So color equals green. And the shape equals an output node. And I'm going to call it leaf out. Leaves out. All right, I'll go up. And so that's cool. Then all we need to do then is pop in a normal SOP after this. So there's a normal for our bark. And then just drop in a normal SOP after here. This is really just dotting I's and crossing T's. And then what we're going to do is merge these two. And there you go. There we have is a bunch of leaves. Going on there. Okay, so there we go. And so now let's put this a null after this and call it tree out. No. Tree out. I'll put the display on that and make a color of green and give it a shape of, let's make it fancy here. This is like big explosion time. Hey, wacky, look at me. There we go. Is it green? Make it green. Green, you bugger. There we go. All right, hit save. All right, there we have our tree action here. And we got lots of leaves here. And now if we really wanted to go nutty, so okay, we've got 20,000. So let's see if we add a whole bunch of leaves. There's a whole bunch of leaves. All right, cool. They're all getting bunched up there. So let's move this away from the bark a little bit. Move it away and move this in a little bit. Okay. And then let's add some more branches. All right. There we go. Now we're starting to look like some real tree action here. Okay. Whew. All right. Now there's still a bunch of other things that we got to do out of here, and we could try to put this into UE4. So next week, I think what I'm going to do is, we're out of time here. I'm going to see if I can slap this into UE4, and I'm going to see if I can add a little bit more things to add a little bit more randomness and a little bit more craziness to this. Right now, it's all kind of like downhill. All the tough part is done because we've got all that tough part. Now we should be able to rock and roll and just go ahead and put this in UE4 and or Unity or whatever package we so chose. And we have lots of trees here. And there's lots of things that we can play with now, lots of places. We can go and play with the bark. So here, all right, is this going to change things? Yes. All right. And we can make it look stupid. All right, there we go. And we're going to add some stupid bark. And yeah, with pinches in it. They look like wiener trees. Okay, good. We're going to have the wiener trees here. And I'm going to get rid of that. I'm going to go ahead and save this and push this up to the GitHub. And so you can go ahead and download that and play with it till your heart's content. And tuned in next week when we will just try to go ahead and add just a little bit more randomness to this and drop this into UE4 and just kind of take a look at it before we get launched on to our next topic. All right, thank you very much for joining me. If you like what you saw today, go ahead and click subscribe to the channel. And for all of those who are in the Orlando area, be warned, we are going to have our first ever Orlando Houdini Users group. It'll happen online probably sometime in the near future, probably sometime in July. So be ready for that. I'm not sure when, but by the end of July, we will have a Houdini Users Group meeting. And I'm going to try to go for something in person, but if not, we'll have it online. And start getting some of your ideas, like come on, introduce yourself. Let's have some fun and show what you want and your needs and desires are with Houdini, and then we can go off with there. All right, great. Thank you very much. Subscribe to the channel if you like what you see. Join the Orlando Houdini Users Group. And otherwise, I will see you next week on Houdini Secrets Live. Arrivederci, gang.